to Physics 100. I am Professor Curtis, your instructor for this course, and this is the video lecture, or lecture video, I guess it works both ways, for Chapter 3, Linear Motion. Let's get started. So, to start off with, I hope you remember scalars and vectors from the previous lecture, because in this lecture we're going to go a little bit more in depth into scalars and vectors, and in particular about the examples that we looked at previously. We listed them, didn't really look at them all that much. Now in this lecture we're going to do just that. We're going to define some of these values, and then we're going to explain how they're related to each other. Start off with, let's take a look at speed. Speed is essentially distance traveled per unit time. So mathematically, we take the distance and divide by the time. Another way to write this would be v equals d over t, where v is the speed or velocity, depending upon if you have a scalar or a vector. D is the distance or displacement, again, depending upon whether you have a scalar or a vector. And t is time, which, for purposes of this class, is a scalar quantity. For those interested in the calculus version, this is what that same relationship looks like. Now, you of course don't have to know any of this calculus to succeed in this course, but I always have students who are curious about the calculus, and so they want to see it, and so that's why I have it here. Again, you don't have to know any of that. Speed equals distance over time, v equals d over t, that's all you really need to know. And as we're going through the different equations here in this lecture, keep in mind that you don't have to memorize any of them. With your test, you will receive in a sheet that lists all the equations that you're going to need for the test, and then some. So you don't have to memorize any of these equations that you're going to be using, but you do have to know how to use them. So keep that in mind as we go through the lecture today. There's two types of speed. The first is what we call instantaneous speed, and this is the speed of an object at a given instant. It's very difficult to calculate instantaneous speed without the use of calculus. And so the only representation I have for you is the calculus. And because that's beyond the stipulations of this course, you don't need to know the mathematical expression, but you do need to understand the concept. Instantaneous speed is the speed of an object at a given instant. The other type of speed is average speed, and it's just as the name implies, it's the average of your speed over a given time interval. So we calculate that by taking the total distance traveled and dividing it by the total time it took to traverse that distance. This then is the average velocity. So, when you get a ticket for speeding, which speed is law enforcement using? Instantaneous speed or average speed? Which do you think? And yes, that means you're supposed to, if you haven't said anything, you need to say something. You know, put your foot down, say, this is where I'm standing, man. And it's okay if it's wrong, because, okay, this doesn't affect your grade, but it's a great place to learn your knowledge gap. So what do you think? Instantaneous speed or average speed? Well, I hope you said instantaneous speed, because if you just look at this and think about it, it would make sense, right? It can't be average speed, because how is the cop going to know the total distance that you traveled? How's the cop going to know the total time that it took you to travel that distance? And the radar gun's not going to say anything about that. So it's got to be instantaneous speed. They're taking the speed of your object, which is the car, at a given instant in time. Now we've looked at speed, let's take a look at acceleration. Acceleration is a scalar, is the change in speed per unit time. Of course, there's also the vector version, but it's the same concept. You just add direction to the magnitude. Here's how we calculate acceleration. It's the change in speed over the change in time. So now we've got the change in the velocity, or the speed, divided by the change in the time. Notice the subscripts on our variables here. V, of course, for velocity or speed. T, of course, is time. But there's a 2 and there's a 1. So what are these numbers representing? Well, representing the velocity or the speed and the time at positions 1 and 2 of our body that's in motion. So essentially, the body that we're studying, whatever that may be, is starting at position 1 and moving to position 2. So the v1 is the velocity at the position 1. v2 is the velocity at position 2. Likewise, t1 is the time at position 1, and t2 is the time at position 2. Of course, if you're interested in the calculus version, here's what it looks like. Yeah, again, you don't have to know the calculus version. I just show this for some students who, every time I teach this class, there's always some students who say, I want to see the calculus. I want to see what it looks like. So there it is. Note that acceleration is the time rate of change in velocity. Some students get this confused. They get confused between velocity and acceleration, between speed and acceleration. We all understand the concept of speed. It's how fast you're going. But acceleration is how fast you're going is changing. So think of acceleration as how fast you're speeding up or slowing down, because that's what acceleration is. The rate at which you're changing how fast you're going. Galileo, again, taking the finish line here for the race, I guess you would call it, through history, of being the first to develop some of these concepts that we're looking at. So, again, a lot of these studies that he was doing while under house arrest involved mechanics. And so his studies led him to develop the concepts of speed, velocity, and acceleration. And, of course, because he's running experiments on all of this stuff, he needs to take measurements to support his assertions. Well, how do you take measurements? Well, again, remember speed, velocity, acceleration. We need to measure distance and we need to measure time. That's how we're doing this. So you've got little trouble measuring distances. I mean, there's plenty of standards you can use for that. And so, especially when you're doing it inside your house, that's not really much of a problem. The problem he ran into was measuring the small amount of time that his experiments were running. The technology of his day didn't really give him much option as far as measuring these small amounts of time. I mean, today we don't think anything out of whipping out a smartphone and then accessing an app on that phone and then using that app, a timer app perhaps, to measure small amounts of time. But Galileo didn't have that option. So what would he do instead of doing what we would do today? What was available to him? Well, sometimes he used his own pulse, so that he used his heart rate as a measure of time. Other times, he used a dripping water clock that he invented for the purpose of keeping time. So it would be drips of water that would come out at regular intervals, and then he would measure drops of water as his time standard. Now, there's some calculations that we're going to go through here with the linear motion, and I'm going to show you how these concepts are related, and then I'll give you a chance to do the same thing. The basic equations that we're going to be using for our calculations come from the calculus, and it was calculus that was invented by Sir Isaac Newton precisely to further his study of mechanics. Again, another reason why Newton was looked at as one of the big great giants of science. He actually invented a new field of mathematics so he could study his particular field of science. Let's look at this example. Suppose a car starts from rest and travels in a straight line under constant acceleration. After 10 seconds, the car is traveling at 44 meters per second. First question we're asked is, what is the acceleration of the car? Second, how far did the car travel in 10 seconds? And third, what is the average speed of the car after 10 seconds? Let's take a look at each one of these questions in turn. So the first question, what is the acceleration of the car? To find acceleration, we go back to the definition of acceleration, which is the change in speed over the change in time. So here we've got our equation, and now we simply substitute the known values into that equation and solve for what's not known. So we start with our equation. we substitute in what we know. So the velocity at position 2 is the 44 meters per second that we see in the problem statement. The car travels from position 1, which is where it's at rest, to position 2, where it's traveling 44 meters per second. So the velocity at position 2 is 44 meters per second. The velocity at position 1 is 0. Again, it's starting from rest. The time at position 2 is 10 seconds. The time at position 1 is 0 seconds. We're assuming we start the clock at 0 seconds. We can actually start it wherever we want, just as long as we're consistent with whatever convention that we adopt. So now we've got the numbers in. So now we just go ahead and plug in. We've got the plug, so now we do the chug. So 44 minus 0 is 44. 10 minus 0 is 10. 44 divided by 10 gives us 4.4 meters per second squared. This is the acceleration of the vehicle. What this means is every second, the velocity or speed of the car is increasing by 4.4 meters per second. Now the second question, how far did the car travel in 10 seconds? To find the distance, we need an equation that relates it with acceleration. Here's a good equation for us to use. x2 equals x1 plus v1 t2 plus 1/2 a t2 squared. So again, remember the subscripts. 1 means you're looking at that variable at position 1. 2 means you're looking at that variable at position 2. So x2 is the distance or position of the vehicle at position 2. x1 is the distance or position at position 1. v1 is the speed or velocity at position 1. t2 is the time at position 2. A is the acceleration, which of course is the same. We're assuming it's the same all throughout, so there's no subscript there. T2 is at the time at position 2, and we're going to square it there in that last term. So now we've got this equation. Let's substitute in what we know and then solve the equation. So we don't know what the position at position 2 is because that's what we're trying to find. How far did the car travel? We know the position at position 1. It's typically we start counting at 0. So we'll start there at 0. The velocity at position 1 is 0. So that's because it starts from rest. The time at position 2 is 10 seconds. Then we have plus 1/2, the acceleration, which we solved in the previous question, 4.4 meters per second squared. And then the time at position 2, again, 10 seconds. So when you solve the math here, you've got 0 for your first term, 0 for your second term, so it's 1/2 times 4.4 times 10, which gives us 220. 220 meters is the distance the car traveled in 10 seconds. Here's the calculus version of what we just went through. Again, you don't have to know, any of this calculus stuff. You do need to know the equations that are boxed. They're very helpful to use. So v2 equals v1 plus at squared, and x squared equals x1 plus v1 t2 plus 1/2 a t2 squared. These two equations are very useful to use for solving linear motion problems. So you want to keep those in mind. Again, you don't have to memorize them, but you do know how to use them. And again, you don't have to know the calculus, but I show this for those students who really want to see it. So if you're one of those students, here you go, eat your heart out. All right, question 3. What is the average speed of the car after 10 seconds? So to find the average speed, let's go back to the definition. We defined average speed as the total distance divided by the total time. So we substitute what we know into the equation and solve it. So total distance traveled, we got that from question 2, 220 meters. The total time we get from the problem statement is 10 seconds. So 220 divided by 10 gives us 22. 22 meters per second is the average speed. Now notice there's a big difference between the average speed of 22 meters per second and the instantaneous speed of 44 meters per second. Big difference there. So there is a difference between instantaneous speed and average speed, and you really need to understand the difference between them so you don't get them confused. Let's move on to an activity now. It's your turn to try out the calculations that we just went through. So imagine you're flying an airplane at a constant speed of 140 meters per second. Your passengers are suddenly in a hurry, so you decide, hey, I'm going to increase the speed to 200 meters per second. You do so at a constant rate, meaning the acceleration is going to be constant, and it takes you 10 seconds to do so. Question 1, what is the acceleration of the plane during that 10-second interval? Question 2, how far did the plane travel in those 10 seconds? Question 3, what is the average speed of the plane during those 10 seconds? Go ahead, stop the video here, and take a crack at answering these questions. And then, when you get done, come back to the video and we'll see how you did. Okay, hopefully you didn't spend too long on that. Let's take a look at the right way to calculate the answer to each of these questions. So, first question, what is the acceleration of the plane during that 10-second interval? Well, if you go back to the definition of acceleration, change in velocity over change in time. So we started at 140, we increased to 200. So the difference between those two is going to be the change in velocity. And the total time, 10 seconds, there on the bottom. So 200 minus 140 is 60, divided by the 10 seconds gives us 6 meters per second squared. This is the acceleration of the plane during that interval. Second question, how far did the plane travel in those 10 seconds? Well, again, we're going to use that distance equation to get out that answer. So we substitute in what we know. x1, typically 0, 140 meters per second. That's your velocity at position 1. The time at position 2 is 10 seconds. The acceleration we got from the previous question, 6 meters per second. And again, 10 seconds is the time at position 2. So the first term is going to be 0. 140 times 10 gives us 1400. 1/2 times 6 times 10 squared gives us 300. So 1400 and 300 then add to give us a total of 1700 meters. This is how far the plane traveled in those 10 seconds. Question 3, what is the average speed of the plane during those 10 seconds? Well, again, go back to your definition. Average speed is the total distance traveled divided by the total time. So the distance traveled is 1700 meters. Time is 10 seconds. 1700 divided by 10 gives us 170 meters per second. So all of this that we're seeing here with these equations we're using to calculate goes back to Galileo and his inclined plane experiments. Yes, Newton invented the calculus that we can use to derive the equations, but it was Galileo's work that led Newton in that direction. So when we're looking at Galileo, okay, we have to remember he's doing these inclined plane experiments. And one of the variables that he changed in his inclined plane experiments was the slope of the incline. And he noticed that as he increased the slope of the incline, as it gets steeper and steeper, and he rolls the ball down, and he observes the motion of the ball as it rolls down. As the incline gets steeper, the acceleration of the rolling ball gets larger and larger and larger, until finally he's got the inclined plane basically going straight up and down, and this is where the value of the acceleration maximizes itself out. And he noticed something very interesting when he got to that position in his experiment, because he noticed that this maximum value of acceleration is the same as when you just let the ball just fall straight down. It's like you don't even need the inclined plane at all. And in this position, acceleration has its maximum value. The other thing he noticed is that whatever it was that he was falling, because remember, he did those experiments from the Leaning Tower of Pisa before the church put him under house arrest. And one of the things that he learned from that experiment was that all falling objects, regardless of size or weight, have the same acceleration. Now, this is where some students get confused. It's not the same velocity. It's the same acceleration. Acceleration, remember, is the change of velocity with respect to time, change of speed with respect to time. How fast you're moving is velocity or speed, but how fast that changes is acceleration. And that value of acceleration is the same for all objects that are falling. Doesn't matter how big they are, how massive they are, doesn't matter. Acceleration, the rate at which they change speed as they're falling is going to be the same. So if we take away forces that would resist the motion of a falling body, like friction and drag, then the only force that's acting on a falling object is gravity. And therefore we can conclude that a falling object is changing its speed because of gravity. Because if we take away those resistant forces and it's still falling, well then gravity must be what's accelerating it, must be what's causing that motion. And so we have what's called acceleration due to gravity. Galileo was observing this acceleration when he was dropping his objects from the top of the Leaning Tower of Pisa. We use the lowercase letter g to represent this acceleration, and it has a numerical value, 9.81 meters per second squared. Now, if you are into the textbook at all, you'll notice that the textbook author simplifies this by using 10 meters per second squared. He's trying to make the math simpler. It's easy to multiply stuff by 10, divide stuff by 10, because all you're doing is moving the decimal point. And he's just trying to make the math a little bit easier by rounding the 9.81 to 10. For purposes of this class, you can use either one. Okay, it is not going to matter which one you use. So if you have an easier time using the 10, use the 10. I'm so used to using the 9.81. That's what I use. And so it doesn't matter what you're going to, it doesn't matter what you use, because the numbers you're going to get out, okay, for your test and whatnot, all your tests are multiple choice. And when you're having to do some kind of calculation with this, the question's always going to be worded like something like, what is your answer most closest to? And so it doesn't matter whether you use the 10 or the 9.81, because either way you'll come to the same answer if you do the calculation right. So yeah, it doesn't matter which one you use. Just take your pick, whichever one you feel more comfortable with. For me, I'm so used to using the 9.81, I just use 9.81. But if you want to use the 10, use the 10. So the equations of motion that we saw earlier are going to apply to falling objects. The only difference is that we have a different value for acceleration. It's g. So we can use those earlier equations. We just substitute g in for our acceleration value, and away we go. So our acceleration equation, remember, was defined as a change in velocity over the change in time. Well, we can transform that by substituting g, and now we've got the acceleration for a falling object. Notice the negative sign in front of the g. That is to remain consistent with our sign convention. Remember, our sign convention for forces says that down is a negative direction. Well, which way is gravity pulling you? It's pulling down. So in order to be consistent with the sign convention, we have to have the negative sign there. We can do the same thing with velocity. That velocity equation that we saw earlier now becomes v2 equals v1 minus gt2. Again, notice the negative sign there to be consistent with our sign convention. And finally, the position distance equation that we saw earlier, we can substitute into that, and now we get the position distance for a falling object, x2 equals x1 plus v1 t2 minus 1/2 g t2 squared. So we can use the same equations of a motion, they apply, but now because we're substituting the g in for the acceleration, now these motion equations are very specific in how you use them. You use them for falling objects, or if you have another body that's got the same acceleration as that due to gravity. But, so now we've got the general equations that we've made more specific for specific application. So let's take a hand at using those equations for the specific application of a falling object. In the spaces in your workbook, go ahead and suppose you're standing at the edge of a cliff. You hold a rock in your hand over the edge and release it. Using your watch, you observe it takes the rock 10 seconds to reach the bottom. How high is the cliff? Well, go ahead, use your equations of motion, stop the video, run the calculation, and then come back and we'll see how well you did with that. Okay, let's see how well you did with that. So, the equation of motion we want to use is that distance equation. So x2 equals x1 plus v1 t2 minus 1/2 g t2 squared. We substitute the values that we know. At position 1, the distance there is 0. Velocity at position 1 is 0 because it's at rest before you release the rock. So it's not moving, so it's at rest. 10 seconds is the time it took to reach the bottom. 9.81 is the acceleration due to gravity. And so we take all those numbers and we churn out the math. The first term is 0. The second term is 0. The third term, negative 1/2 times 9.81 times 10 gives us a negative 490.5 meters. Notice that distance is negative. What does that mean? Well, that just means you're on the other side of 0. Remember, to be consistent with our sign convention, down means negative. To the left means negative. Well, you're dropping a rock and it's in free fall as it goes down the edge of the cliff. So down is a negative direction. So that's all the negative sign is indicating, that the distance of 490.5 meters is a negative displacement. It's in the negative direction. And that brings us to the end of this lecture video. I hope you found it helpful. Thanks for watching, and I will see you in the next video.